Alright, now that we have limits, we can talk about derivatives because all the formal tools are in place. As we go through this presentation, you will notice that just about everything we do could have been done in a calculus class and probably has been done in some form in a calculus class, except that usually proofs are not emphasized in a calculus class in the sense that you're also requested to do proofs on a regular basis on the homework. So if you already had a bit more emphasis on the proofs in a calculus class, then this presentation will be easier for you. If not, you still went through a good calculus class. The purpose of calculus is to produce people who can apply mathematics, not to produce people who do proofs, at least in my opinion. Well, and now let's just get to it and see what's going on with it. Okay, so when we take derivatives of complex functions, basically the idea still remains the same. The idea, the idea has the same root. The idea for derivatives was the desire to compute instantaneous velocities or slopes of tangent lines. And formally that means in both cases we want to know what happens when this denominator h in the difference quotient f of x plus h minus f of x divided by h goes to 0. Now, for complex functions, the visualization is challenging if I want to say that charitably. For me personally, it's actually impossible because I can't visualize a four-dimensional graph. Remember, two input dimensions, two output dimensions, and then some kind of tangent attached to it. But we can investigate the very same question about what happens to this difference quotient also for functions that map complex numbers to complex numbers. After all, the algebra, well, we can form differences, quotients, and all that in complex numbers, as well as the idea of a limit, which we've just talked about in the previous presentation. All that translates to the complex numbers, so the computations ought to really be the same. Okay, so definition: if we have a function that is defined in a neighborhood of the point z0, then f is called differentiable at z0, if and only if the limit as z approaches z0 of f of z minus f of z0 divided by z minus z0 exists. Again, notice that we didn't mention complex numbers here because implicitly in complex analysis, of course, we assume that our functions map complex numbers to complex numbers. But other than that, this is verbatim the definition from calculus of a differentiable function. You want to know what happens to the quotient of the differences in the outputs divided by the differences in the inputs as the two inputs get closer to each other. In this case, we set the derivative to be f prime of z0 being equal to that limit, just like in calculus. And we call it the derivative of f at z0, so really nothing changes. And the notations are also the same. We'll call that df dz at z0 or df of z0. I don't think we'll use the capital D at all in this course, but sometimes people also write the derivative like that. Okay, a function f with an open domain is called differentiable or holomorphic or analytic. And these two words are very often used interchangeably in complex analysis. And even though there is a technical difference, or even though a technical difference between those two terms can be made in a broader context, typically in a complex analysis they're used interchangeably. And we will stick with analytic throughout. If and only if the function is differentiable at every z0 in its domain. Now, we're a bit more technical here. We demand an open domain because basically what we want to be able to do is when we take a derivative at a point, we want to be able to go in every direction around that point for at least a short distance. And that's just something that ultimately helps with the theory. The function is called entire if and only if it's differentiable at every complex number, every point z in C. And if f is not differentiable at z0, but for every neighborhood of z0 there is a point so that f is analytic in a neighborhood around that point, then z0 is called a singularity. Now that's a very technical definition. Again, the typical singularities that we will be looking at later in the course are situations where the function is defined on a deleted neighborhood of z0. It can be proved, and that's a fairly quick argument that may have been assigned as a homework problem, that the function f is differentiable at z0 if and only if the limit as delta z goes to 0 of f of z0 plus delta z minus f of z0 exists. And that's because if you call z to be z0 plus delta z, well, then z minus z0 is just a delta z, and then when z goes to z0, then delta z goes to 0. So this is just a quick translation using the definition of limits. In this case, then, of course, because the translation is so direct, this limit here is the derivative. And with our typical notation that w often denotes the output, we would have that delta w is the numerator of this difference quotient, and then we also write dw dz being the limit delta z going to 0, delta w over delta z. That z probably should be larger than it is here, but it's a delta z going to 0. Okay, now the z actually is large. I just fixed that real quick. That's, of course, a negligible contribution, but nonetheless, at least now it looks right. Okay, what can we do with that? Well, first of all, again, notice that just like in calculus we had dy dx, now here we've got dw dz, so everything is very, very similar, and aside from our reference to complex numbers, this is really exactly what you did in calculus, only now we put more emphasis and pay more attention to the abstract parts rather than the straight application of differentiation formulas, which we'll also get to. Okay, example, well, compute the derivative of f of z equals z cubed. How does that go? Well, dz cubed over dz, we just have to go to the definition of the derivative, because technically right now we don't have any other formulas, any other avenue to compute derivatives available to us. And so we get that this is the limit as delta z goes to 0 of z plus delta z cubed minus z cubed divided by delta z, those wonderful difference quotients from your first calculus class that you may remember fondly or not so fondly, and you also remember what comes next. Now we just have to somehow get this into a form that we can cancel the delta z in the denominator, because we can't divide by 0 as delta z goes to 0. First step, we multiply out the parentheses, so for cubes we get z cubed plus 3z squared delta z plus 3z delta z quantity squared, I guess, plus delta z cubed, because delta z is considered a compound symbol. You typically don't put parentheses around that. The minus z cubed is still from the top, and then we divide by delta z. The z cubed and the minus z cubed goes away. That leaves us only with terms delta z in the numerator, which is what should happen if the derivative can be computed. And then, to be absolutely sure, I know we can start canceling here if we want to, but to be absolutely sure, to avoid any kinds of problems, I typically suggest that we explicitly factor out the delta z to get the limit delta z goes to 0, delta z 3z squared plus 3z delta z plus delta z squared divided by delta z. Now we can cancel the delta z, and then with delta z going to 0, of course, only the 3z squared here survives, and so the derivative is 3z squared, which should not be a surprise, because that's what the derivative of x cubed is. It's 3x squared. And because the algebra and the limits all work the same way, and because this function in fact extends the function x cubed, which goes from r to r, to a function that goes from z to z, it would be extremely surprising if we would really get something substantially different than 3z squared here. In fact, it would be extremely surprising if we got anything different than 3z squared there. Okay, we can also show that functions are not differentiable, and that's where really difference quotients are the only choice. So show that f of z equals c bar is not differentiable at any z0 in c. Well, then the limit as delta z goes to z. So in order to show that, we again just attempt to compute the derivative, and we show that something's going wrong and that limit doesn't exist. So the limit delta z to 0 of z0 plus delta z bar minus z0 bar over delta z. Well, we know the difference of conjugates is the conjugate of the difference, so this is the limit as delta z goes to 0. z0 plus delta z minus z0 bar divided by delta z. That's the limit as delta z goes to 0 of delta z bar over delta z. And we have seen that that limit does not exist. That was part of the previous presentation. And because that limit does not exist, that means that the function is just not differentiable, and because z0 is arbitrary, it's not differentiable at any complex number z0. Okay, some abstract theorems that we also may or may not remember from calculus. If a complex function is differentiable at a point, then the function is also continuous at that point. And that means every differentiable function, every function that is overall differentiable, is continuous overall. And on the other hand, and this is the typical thing where we can explain that A implies B does not imply that B also implies A, not every continuous function is differentiable. And the proof, well, again, this is one of those proofs where at the end we see where the idea comes from. For continuity at z0, note that 0 is equal to, well, 0 is equal to the limit as z goes to z0 of z minus z0. And if I multiply that with any number, and because the function is differentiable, this thing is a number, that's still 0, so that's correct. But the product of two limits is the limit of the product. And z minus z0 cancels now, so this is the limit as z goes to z0 of f of z minus f of z0. Well, and that means, that the limit as z goes to z0 of f of z is equal to f of z0, because now the limit of f of z0 is just f of z0, and we can bring that over. So the idea of the proof was to show that, well, continuity at z0 means that f of z goes to f of z0, which means f of z minus f of z0 goes to 0. And then the one trick there is in mathematics, right? Multiply, well, one of the two tricks, multiplying by 1 or adding 0. We multiply by 1 and then puzzle things apart to realize that that's 0. Okay, for the last statement, we would simply have to consider the function f of z equals z bar. That function is continuous, but as we have seen on the previous panel, it is not differentiable. In fact, it's not differentiable anywhere. Okay, well, that's that one. And now we're going to talk about differentiation formulas. Well, if we take two differentiable functions that are differentiable at z0 and let c be a complex number, then the functions f plus g, f minus g, and c times f are all differentiable at z0. That is something that we also know and recall from calculus, and the same differentiation formulas work out. The derivative of a sum is the sum of the derivatives. The derivative of a difference is the difference of the derivatives. And constants can be factored out of the derivative. The proof, all those proofs are very similar. Some of them may even be assigned as homework problems. Let's take a look at the proof for addition. So the derivative of f plus g would be, we just go back to the difference quotient. It's the limit as z goes to z0, f plus g of z minus f plus g of z0, divided by z minus z0. And f plus g, well, that's f of z plus g of z, and similarly here we get minus f of z0 plus g of z0. And now, because we want to compute the limit, let's look for patterns. We assume that f and g are differentiable, and that means a difference quotient f of z minus f of z0 divided by z minus z0, and a quotient g of z minus g of z0 divided by z minus z0. That is something that we ought to be able to work with. So we simply resort the numerator, and we get that this is f of z minus f of z0 plus g of z minus g of z0. And we can split those fractions apart, so that's the limit as z goes to z0, f of z minus f of z0 over z minus z0 plus limit z going to z0, g of z minus g of z0 over z minus z0, and that's f prime of z0 plus g prime of z0, because f and g both were differentiable at z0. So the idea is actually quite straightforward. You first set up the limit that you need to compute, you simplify it as much as you can, and then you start looking for difference quotients that you know the value of, or the limit of. Okay, similarly, the product and quotient rule, if f and g are differentiable at z0, then the product is differentiable at x, and the derivative of the product is f prime times g plus g prime times f. And if g of z0 is not equal to 0, then the quotient f over g is also differentiable at z0, and the derivative is f prime times g minus g prime times f divided by g squared, all of that evaluated at z0. So notice here that as I talked my way through this, I suppressed the arguments. That's just fewer symbols to remember. We know we evaluate all that at z0, just as we know in calculus that we evaluate everything at x, let's say. And the other thing that I typically tell in calculus, and that is also worth telling here, it makes sense to remember that the product rule is essentially the numerator of the quotient rule, only with a plus. That way, in some ways, I think when I was a student, I really only memorized the quotient rule and knew that the product rule was the numerator with a plus. And the other thing is, that way you remember them in the same order, because every so often, of course, somebody on a calculus test or even later confuses the order here because they've memorized the product rule in the opposite order. And for the product rule, that doesn't matter, but for the quotient rule, it does. Okay, so these are all fairly little simple things, and now in this more abstract setting, well, we want to prove things, and we're going to prove the quotient rule. The proof of the product rule is similar, but I think easier, and again, it may well be a homework problem in this class. So, but let's take a look at the quotient rule. And what did I say in the simpler proofs for sums? You first just set up the difference quotient. So the limit as z goes to z0, f over g of z minus f over g of z0 over z minus z0, we know what that is. That's the limit as z goes to z0, f of z over g of z minus f of z0 over g of z0 divided by z minus z0. Well, that's fractions inside fractions, so it's very natural what to do next. We've got to find common denominators and turn everything into one fraction. Alright, so finding common denominators, multiply with g of z0 here and multiply with g of z here, we get limit z going to z0, f of z g of z0 minus f of z0, g of z divided by g of z times g of z0 divided by z minus z0. And then we can go ahead and multiply with the reciprocal of z minus z0. And I want to pull the g of z times g of z0 out, so I end up with the limit z going to z0, 1 over g of z times g of z0, f of z g of z0 from here minus f of z0 g of z from here, divided by z minus z0. That's just straight simplification. Okay, now we need a little bit of ingenuity, if you will. We split this part off because basically this will go to 1 over g of z0 squared. And even if we didn't already know the result, that looks like a limit that we just want to keep separate. These are the guys that we have to deal with, because here's where we have differences. And again, we would like to factor stuff out. We've got a difference of two products, but the products have no common factors. Well, I think I mentioned earlier on in the previous presentation that when that happens, it helps to add and subtract a mixed term, and that's exactly what we're doing in the next step. So this looks quite big, but we kept the 1 over g of z minus g of times g of z0, kept the f of z times g of z0, kept the minus f of z0 g of z here, kept the division by z minus z0. Then we just took the f of z0 and the g of z0 and subtracted that product and added it in the same breath. One of the two tricks in math, we've added 0. And that means this is the same. And we can also sort of see why we do that, because now we can regroup and then factor things out. Here's where we can factor out g of z0. Here's where we can factor out f of z0. Okay, so that means we already have them grouped the right way, but we'd like to have difference quotients ultimately, so we just leave the front the same and just turn this plus into a minus parentheses and then keep all this stuff here. And well, that means that minus f of z0 g of z now comes up front, and f of z0 g of z, which was a plus, becomes now a minus minus. Other than that, it's the same thing. And now we break up those difference quotients. So again, 1 over g of z0 stays the same. And now this minus sign is just this minus sign, and we just broke the fraction up into two fractions. Okay, now we're out of paper. Don't worry about that. This is the same thing as what we had in the last line on the previous panel. And so now what can we do here? We can factor out g of z0 here, we can factor out f of z0 here, and that's what we're doing. So this is the limit as z goes to z0, 1 over g of z, g of z0, f of z minus f of z0, z minus divided by z minus z0, g of z0 minus g of z minus g of z0 divided by z minus z0, f of z0, and now we can take the limit, and so this is 1 over g of z0 squared because of continuity. This difference quotient converges to f prime of z0, g of z0 of course stays where it is. This difference quotient converges to g prime of z0, and f of z0 stays where it was before, and that's exactly the product rule. Okay, theorem, next theorem here. Oh yeah, sure, we also need a chain rule, right? And I should call that the chain rule. Let me call that the chain rule. Okay, so here's our theorem, and it is the chain rule. And we let f and g be complex functions. We let z0 be so that g is differentiable at z0, and so that f is differentiable at g of z0. Well, then the composition is differentiable at z0. I gave myself away here. Apparently, I've copied stuff from notes that I had on functions of a real variable. But then again, I've said all along that all these computations are very, very similar. So there's no crime in that. I just need to make sure that my slides work out. Okay, then the composition is differentiable at z0. And the derivative is f composed with g prime at z0 as f prime of g of z0 times g prime of z0. So the chain rule is exactly the one that we are also familiar with from calculus. And the proof, well, let's talk our way through the proof, and I will have to tell you a little bit more about why we're ignoring a small technicality here. Let's go through the proof in the most natural way, in the most natural way to start the proof, which would be that we take the limit as z goes to z0, f composed with g of z minus f composed with g of z0 divided by z minus z0. That's the limit as z goes to 0, f of g of z minus f of g of z0 divided by z minus z0. We'd like to have difference quotients. Well, g of z minus g of z0, if we, because g is differentiable at z0, g of z minus g of z0 goes to 0, so we could make that a denominator in a difference quotient, and of course a difference quotient g of z0, z minus g of z0 over z minus z0 is also something that we can control, so multiplying by 1 here seems to be a good idea. Then we sort that out. This is the limit as z goes to z0, f of g of z minus f of g of z0 divided by g of z minus g of z0 times g of z minus g of z0 divided by z minus z0. And those limits then, of course, the limit of the product is the product of the limits. And then I can also simply call g of z u, and when z goes to z0, then that u goes to g of z0. So now we really have a difference quotient of f at g of z0 here. The latter difference quotient for g stays the same, and then this is f prime of g of z0 times g prime of z0. And that, well, that looks like a proof, and it feels fairly convincing. The problem is that this expansion can only be done if g of z is not equal to g of z0. So there is a technicality here that we are not taking into account, which is what happens if there is a sequence of zn's, let's say, that goes to z0, so that g of zn is equal to g of z0. That would require a separate argument that actually gets rather technical. In my blue text on analysis, we actually works that out for functions of a real variable. The other way, which is very elegant, which Churchill and Brown are choosing, is a typical complex analysis proof. They choose a certain auxiliary function that you may not really be able to figure out where they get it from, but that auxiliary function makes everything work out, and of course the idea is that that auxiliary function avoids the technicality here. Okay, we're not going to go into those technicalities, and we're also not going to go through the magic of that auxiliary function, so we're simply going to say that this proof is, for our purposes, done. We're also not going to prove the power rule here, because that's something you can do with induction and with the product rule. It's a very nice proof there, and so now we're just saying we're done with this one, and we're going to just look at some examples to round out this presentation. And the example could have come from calculus. Basically, we want to drive home the point that derivatives work just like they did in calculus. So let's say we want to find the derivative of the function f of x equals iz plus 4 quantity cubed times z squared plus 1 quantity squared. And of course, we don't want to multiply all that out to work it out as a polynomial. Instead, we take the derivative of this thing with the product rule, and that's a product rule and a chain rule, right? So we need that this is, first of all, the derivative of the first, which is 3iz plus 4 quantity squared times I, and that's by the chain rule, times the second function, which is z squared plus 1 quantity squared, plus the first function copied times the derivative of the second, which by the chain rule is 2 times the inside z squared plus 1 times the derivative of the inside, which is 2z. And then we can factor that a little bit. Typically, there isn't too much we can do in the way of simplification, but because we'll always be interested in zeros of functions, if we have a chance to factor stuff, obviously, or sort of obviously, then we should take that chance. So here we can factor out an iz plus 4 squared and a z squared plus 1. And, well, yeah, okay, first of all, we clean things up. The 3 and the I becomes a 3i, and the 2 times 2z becomes a 4z. Now we factor out an iz plus 4 squared and a z squared plus 1. That leaves us with, from the first one, 3iz squared plus 3i. And from the second one, it leaves us with 4iz squared plus 16z. And then we just add that up here. The iz plus 4 squared and the z squared plus 1 stays the same. The 3iz squared plus 4iz squared gives us 7iz squared. We keep a 16z and a 3i. And that's it already. So, take a look at what we're doing with differentiation formulas. When you take derivatives, notice that except for the fact that our variable is now called z rather than x, all the rules apply exactly like they did in calculus. And if you have imaginary units in there, if you've got i's in there, remember that they act just like constants, so that should not be too much of a problem. The other thing that you'll do is you'll probably prove some differentiation formulas. That, again, is new ground. But after the rather nasty proofs about limits, I think proofs of differentiation formulas will actually feel a whole lot simpler. And that's not a bad thing. So on one hand, I'm saying simpler, not simple, but at the same time, basically from the vantage point of having some more advanced training, we can now do more complicated tasks, hopefully with greater ease than we could have done them at the beginning of this course. Alright, thanks a lot. Alright, now that we have limits, we can talk about derivatives because all the formal tools are in place. As we go through this presentation, you will notice that just about everything we do could have been done in a calculus class and probably has been done in some form in a calculus class, except that usually proofs are not emphasized in a calculus class in the sense that you're also requested to do proofs on a regular basis on the homework. So if you already had a bit more emphasis on the proofs in a calculus class, then this presentation will be easier for you. If not, you still went through a good calculus class. The purpose of calculus is to produce people who can apply mathematics, not to produce people who complex numbers here, because implicitly in complex analysis, of course, we assume that our functions map complex numbers to complex numbers. But other than that, this is verbatim the definition from calculus of a differentiable function. You want to know what happens to the quotient of the differences in the outputs divided by the differences in the inputs as the two inputs get closer to each other. In this case, we set the derivative to be f prime of z0 being equal to that limit, just like in calculus, and we call it the derivative of f at z0, so really nothing changes. And the notations are also the same. We'll call that df dz at z0, or df of z0. I don't think we'll use the capital D at all in this course, but sometimes people also write the derivative like that. Okay, do proofs, at least in my opinion. Well, and now let's just get to it and see what's going on with it. Okay, so when we take derivatives of complex functions, basically the idea still remains the same. The idea, the idea has the same root. The idea for derivatives was the desire to compute instantaneous velocities or slopes of tangent lines. And formally that means in both cases we want to know what happens when this denominator h in the difference quotient f of x plus h minus f of x divided by h goes to 0. Now, for complex functions, the visualization is challenging, if I want to say that charitably. For me personally, it's actually impossible because I can't visualize a four-dimensional graph. Remember, two input dimensions, two output dimensions, and then some kind of tangent. A function f with an open domain is called differentiable or holomorphic or analytic, and these two words are very often used interchangeably in complex analysis. And even though there is a technical difference, or even though a technical difference between those two terms can be made in a broader context, typically in a complex analysis they're used interchangeably, and we will stick with analytic throughout. If and only if the function is differentiable at every z0 in its domain. Now we're a bit more technical here. We demand an open domain because basically what we want to be able to do is when we take a derivative at a point, we want to be able to go in every direction around that point for attached to it. But we can investigate the very same question about what happens to this difference quotient also for functions that map complex numbers to complex numbers. After all, the algebra, well, we can form differences, quotients, and all that in complex numbers, as well as the idea of a limit, which we've just talked about in the previous presentation. All that translates to the complex numbers, so the computations ought to really be the same. Okay, so definition: if we have a function that is defined in a neighborhood of the point z0, then f is called differentiable at z0, if and only if the limit as z approaches z0 of f of z minus f of z0 divided by z minus z0 exists. Again, notice that we didn't mention